Welcome to the Carbohydrate discussion series where we explore fascinating world of sugars, polysaccharides and glycochemistry. In today's episode, Bharat Singh Patel will discuss stereoselectivity in glycosylation with deoxofluorinated glucosazide and galactoside thiodonors. Let's begin the session.
Good morning, everyone. Today I am going to discuss the stereoselectivity in the glycosylation with the deoxofluorinated glucosazide and the galactosazide thiodonors. So basically, in this paper, what they have done, they have taken this two C2azide glucose thioglycoside donor and the galactose donor. They have activated this thyroid donor, and they have taken different type of acceptor to see the stereoselectivity outcome. So before coming to the reaction, we'll discuss why they have taken this fluorinated sugar. So as we know, like in case of the replacing hydroxy group with the fluorine, that will not affect too much the chemical and the physical property of the carbohydrate, because this van der Waals atomic radii is comparable, that is 1.47 versus 1.52 in case of fluorine, and the electronegativity is also very much comparable. Not only that, the fluorine, if you see the size of fluorine compared to the hydroxy, that is very much nearable. So that will not affect the metabolic pathway by any animal. And also, after putting this fluorine group in the carbohydrate moiety, so in case of carbohydrate protein interaction, that can be done by using NMR also, where this fluorine group can be monitored by using 19F NMR. So to synthesize that fluorinated carbohydrate sugar, so we have to know not only the reactivity or the how this selectivity will be the donor and acceptor, but also we need to know what will be the outcome of the anomeric stereoselectivity in the glycosylation. Because by replacing of the fluorine, by replacing the hydroxy group by fluorine, it will affect the anomeric stereoselectivity by multiple effects, like the destabilization of the cationic transition state by inductive effect of the fluorine, stabilization of the transient oxocarbenium ion by conformation of electrostatic interactions with the CF bond dipole, and also attenuation of the hydrogen bond acceptor capability with the respect of the parent oxygen substituent. So here they have taken this 4 thiodonor. In case of glucose, they have taken the C3 and the C4 fluorinated thioglycoside donor, and the same for the galactose also, C3 and C4 functionalized fluorine functionalized galactose thioglycoside donor. So here they have masked this C2 position with the azide group, because like in case of beta linkage, that is very much known by NGP. If there is at C2 there is ester functionality present, but in case of azide, that will not guarantee, that will give only alpha, but there will be role of the donor as well as the acceptor for the outcome of this glycosylation of this donor. In case of glucose, this 1,2 donor, in that case, the donor outcome will depend upon the what will intermediate will form. But in case of galactose, along with the intermediate, the acceptor nucleophility also matters for the outcome of the stereoselectivity of the anomeric linkage. So before coming to the the reactions, they have prepared this donor by started with this anhydrous sugar 5. They have changed this hydroxy group by fluorine by reference 20, where they have just maybe taken this protection of this with a triplet modification followed by this dust or some fluorinating agent. And then for the C3 galactose glucose donor, they just use the phenyl trimethylsilyl sulfide in the zinc iodide to opening of this acetal, followed by the thioglycosylation. It will lead the thioglycoside. And the case of C3 fluorinated sugar, they first deprotect this OBN group by using sodium bromate and sodium thiosulfate in ethyl acetate, and then after the deprotection of the OBN group, they change this like orientation of the hydroxy group by using triflic anhydride followed by the potassium nitrite. Once this orientation of hydroxy group changes, then they just open up this acetal group by using same condition phenyl trimethylsilyl sulfide in zinc iodide. So here they were able to separate out alpha and beta in both cases, like glucose and the galactose thioglycoside donor. In case of C4 thioglycoside donor, they started with the acetal and epoxide protected 111, and then this opening of this epoxide followed by this BN protection of this free hydroxy by using BNBr and sodium hydride. Again, this opening of the acetal lead out to the C4 fluorinated thioglycoside. So here they were not able to purify, separate out the alpha and beta, so they went with the alpha beta mixture. And in case of C4 galactose fluorinated thioglycoside, they started with the 15, opening this C2C3 epoxide followed by this opening of the acetal using same condition. So they got the alpha beta separated C4 fluorinated thioglycoside donor. So to see this reactive intermediate species, they pre-activated the donor by using diphenyl sulfoxide in triflic anhydride using deuterated dichloromethane at -78 degree. So they have taken this C3 fluorinated beta glucoside as, so here if you see at 193 K, there are all the alpha triplet, alpha sulfonium as well as this beta one, all are represented. As the temperature increasing, so they are decomposing, and after -30, -40 degree at 253 Kelvin, it formed this anhydrous sugar 6. And also they have characterized this intermediate by using the NMR, where the reference value are known. So let's say in case of C3 fluorinated thioglycoside, glucose thioglycoside, the coupling constant of 3 atom, that was 10. That means that is the, sorry, here is this 3.6, that is alpha linked, and also this C1 carbon is 104.6. In case of beta, it came down to 102. So maybe here the alpha triplet having more desealed carbon, as well as this triplet having affecting more desealing at the C1. So it's coming lower chemical state value compared to the beta sulfonyl intermediate. Similarly, they have taken other donor like C3 of galactose. They, for alpha triplet, they have calculated this 3 bond coupling constant 4, and as well as this C1 carbon chemical state value. And they have given the temperature, at which temperature this intermediate getting decomposed. And after decomposition, every time this forming this intermediate 6, that is acetal anhydrous sugar. So after that, in pre-activation of intermediate, they knew like what will be the intermediate, in which intermediate this reaction will proceed. So they have taken different acceptor starting with 1 and 2, where this 3 like 1 hydroxy nucleophile they have taken. That means the nucleophilicity of hydroxy group is more. Then 3 to 5, those are the equatorial hydroxy, secondary hydroxy group. Those are less reactive than 1 and 2. And then they have taken pentose furanose sugar also, where axial hydroxy oriented one. And then 7, 8, 9, they were those having the axial hydroxy group, as well as those are secondary also. These are the least reactive acceptor they have taken. So coming to the like most reactive acceptor 1 and 2, in case of glucose, like C3 fluorinated and C4 fluorinated. In case of reactive acceptor, so beta was forming more. That means it is going through the alpha triplet where the SN2 reaction is taking place. But as coming down in the 3, that is benzylidyl protected one, that in that case, this outcome of the selectivity that is reduced. In case of pi, that is even come down. But here C3 to C5, it coming down, maybe the steric region of the benzidine protected one, that is giving beta selectivity. The triplet is the way of activation is SN2 only. But in case of axial hydroxy acceptor, so there is no much stereoselectivity, because there is no role of the acceptor as such. The only way here this little more in the selectivity beta is more because of the way of intermediate is getting activated, or the which intermediate is more stable. So that we'll discuss in later. But if you see the galactose case, where the nucleophilicity of the acceptor matters a lot for the outcome of the glycoside linkage. So in case of 1 and 2 means the reactive acceptor, the beta is more. And once coming to the C3 3 acceptor C, where alpha is more, that means once the nucleophilicity of this acceptor is decreased, so there is no, it's not going through the SN2 mechanism, that is following SN1 mechanism or the solvent separated like SN1 mechanism. The intermediate is not the alpha triplet, that is going another intermediate. So coming C3 to C acceptor to the 4, where D, they have just removed this benzylidine group, they have taken methyl ether. In that case, this outcome is got reverse. Like here alpha was more, here the beta is more, or there is no like no much stereoselectivity, because here again the steric hindrance of this benzylidine matters for the outcome of this selectivity. But coming down to C5 5, 6, 7, 5, 6, since these axial and the furanose sugar, these are least reactive, so there is no selectivity in the outcome of the product. But in case of 7, 8, 9, the beat alpha is more. Alpha will form more when the intermediate will get attacked by either this intermediate. So here they have taken this galactose only for the mechanics studies. They have taken this acceptor. Once this intermediate form, like alpha triplet, if the nucleophile attacking here only, that means it will attack when the acceptor will be like reactive acceptor. That means a strong acceptor. Means case of 1 and 2 there, where there is one primary hydroxy were taken as acceptor. In that case, only the SN2 attack will be happen. But other than that, in case of this one, alpha alpha contact and pair, even though this will follow the SN2-like mechanism, but in that case, alpha product will form. And here also, if we see this intermediate, the half chair 4H3 opening can be done both sides, but this opening will give the chair form conformation. So that's why this will give the SN1-like mechanism, and alpha will be more, like in case of this 7, 8, and 9. And this intermediate is not stable, so it will not give the beta. So it going through the this intermediate. And here similarly for the glucose, if you see glucose, so after these two donor acceptor, there is no such stereoselectivity because it's going via this IISc half-boat conformation. So here the nucleophile can come from both sides, and since nucleophile can come from both sides, so there will be no much stereoselectivity, since at the equilibrium all the intermediate will be there. So like the major role of the outcome will be decided by this IISc boat conformation to SO, as well as the alpha triplet also. They have given all the triplet intermediate and with energy. If you see the case of glucose, these two were most stable one, intermediate. So that's why there is no outcome, there is no selectivity of the outcome of the glycoside product, because it can open in both ways. So after that, they wanted to do some application to synthesize some kind of glycoconjugate. So they have taken 4 donor. They have activated that donor by using similar way, using triplylic anhydride, diphenyl sulfoxide, and they taken acceptor chlorotriethylene glycol. They were able to separate out alpha and beta. Again, they modified this azide group to the NHAC by using thioacetate, followed by this SN2 reaction of this chloro to make it azide. Further, they couple with azide by using click chemistry. As well as they have taken this B3 donor, activated the same way. They have taken this acceptor. They got this disaccharide, again opening up this acetal by using acetic acid. They got this disaccharide. So in conclusion, they have discussed the outcome of the product, which led by the alpha triplet as well as the both anomers of the oxosulfonium triplet. And the case of galactose, where that is the galactose donors, where the acceptor nucleophilicity matters and selectivity for the glycoside donor, glycoside product. In case of glucose as a donor, where the loss of the selectivity, beta selectivity, because of the way of because of the activation of the intermediate that is going through the IISc port conformation.
Bharat bhai, nice presentation. So basically, if the acceptor is more nucleophilic, then it will give beta. It will undergoes to the SN2 reaction.
Yes, if you are using activating through the triplet, any triplet source, in that case, alpha triplet will form. The alpha triplet is the most stable intermediate of the glycosylation.
Okay, alpha is forming, but if the acceptor is less nucleophilic, then it can go from the another one, SN1 mechanism.
Exactly. So if alpha triplet is forming, if it is triplet, so it will form alpha triplet only. If it is alpha triplet and nucleophilicity of acceptor is more, so here only a SN2 reaction will happen, that will give the beta product.
Okay, and in case of alpha product, nucleophilicity is less, it will undergo to the again oxocarbonium ion. And then further
that will be, yes, equilibrium. So this triplet is equilibrium with the contact and pair and this board form and the half chair form. So there are like intermediates. So which intermediate will be stable one? and also that will lead the stable product also in that intermediate that reaction will go. So like here, these two, this one is more stable, and also there is two possibility to open up this one. Like half chair, there is two opening, right? Both side can attack,
Yes.
but
Yes.
this attack only give the chair confirmation. So that's why alpha product is forming.
And how they are justifying these structures exactly, like pathway is going through this way.
So now if you see, like there are a lot literature. Previously we have discussed also
Yes.
this how this strip intermediate they have like track by using NMR, different kind of NMR, and also here they have also did all the data by literatures also, all the intermediates. They have given this C1 carbon chemical shift value as well as the coupling of 1, 2, 3 at 3 bond coupling also. So here, if it is alpha, that coupling constant is coming less than 5, 3.6 and 3.5. If it is beta, then coupling constant is going 8.3.
I don't understand exactly the role of fluorine. I don't
Role
know, I
of?
missed something. Role of fluorine. Something I missed, I think.
No. So in case of hydroxy, there will be some kind of protection and protecting group, right?
Yes, yes.
So these intermediates forming, so as I told in the first slide itself, so there will be these multiple factors that will affect the intermediates, like
Okay.
inductive effect, hyperconjugation, as well as electrostatic interactions. So this isn't intermediate because of fluorine. This intermediate is more stable.
Okay.
Otherwise, in case of hydroxy group, that protected sugar may be another configuration, may be stable one. Because see, this fluorine is like small in size, and as well as it can accommodate any kind of like pseudo axial and equatorial also can be deal with the fluorine in case of this half chair conformation.
By the way, we have
in,
seen. Yes, Devabhai.
in case of all the donors, like they are using this half chair is only more stable
Yes.
intermediate.
Yes.
Okay, then based on the acceptor nucleophilicity, they are getting change in the selectivity.
Yes, in case of galactose, based on the acceptor. Yes, in case of galactose, the acceptor nucleophilicity matters, but in case of glucose, that is not matter a lot. But just a primary, obviously, that will give the major stereoselectivity. Other than the 1 and 2, this primary one, so there is no role of acceptor in case of glucose. But in case of galactose, that even matters.
So basically, they are introducing fluorine to remove the effect of C3 hydroxy group or protecting group.
Yes.
But directly
Yes.
there is no role of fluorine.
No. There is no role directly. Yes.
Because in the sum of the paper they will present the moment they will introduce fluorine, obviously it doesn't have the NGP and other thing, but electronically sometime it will help in the stabilizing the particular conformation or particular reactivity
Intermediate.
pattern.
Yes.
Okay. So here when you are explaining about 5 and 6 acceptor, when it is changing from the equatorial to axial hydroxy acceptor. So in that case, selectivity is getting like little bit reduced in 4E and 4F.
So as per their explanation, when they have taken this equatorial one, so what they have claimed is
It is more nucleophilic. That's
so unhindered second, like the A and B, these are the primary one. Those are the more reactive one, primary hydroxy, primary alcohol.
yes.
Then the less reactive will come as the equatorial one, like the 3, 4, and 5. And the
Yes.
least reactive, the axial one, G2I. But in case of 6, they haven't explained too much, just for glucose. So it's not going through the acceptor nucleophilicity. So there is no also like control also, there is no selectivity also, that is very poor selectivity. But it's getting reverse in case of 4E to 4F. But they have compared this 3 to 4. This benzalidine one, they haven't explained this 5 to 6.
Okay. Basically, in case of 6, they are getting in 4F, they are getting better selectivity than 4E.
Yes.
Okay. So in this 4, they are taking donor as a alpha beta mixture.
4, yes, sir. 8 minutes. Confirm. So, no, 2 they have taken as a alpha beta mixture. 4 is the pure they have taken.
Basically, that they are doing to just to check the selectivity pattern only, right?
Yes, nothing else
In
other
one
than
case,
that.
they are.
So now this technique is available, how to control, like determine this intermediate. So based on that, they're pre-activating the donor, whatever donor they have taken, and then they use this acceptor, and also doing this, they are just taking the base this TMBP, so that there will be no configuration exchange like alpha beta exchange. So whatever alpha is forming in that like intermediate ones, that they are trapping with the acceptor itself, and also whatever acid generating, that they are quenching with the base. They are claiming that like whatever intermediate is forming, they are tracking track with the acceptor. Just they are doing workup and recording.
Here they are showing about the products, right? This alpha beta ratio of the product.
Yes.
Yes. And maximum they are getting in 9 row 4I, that 20 as 1. Alpha is more.
In case of galactose.
No, in case of mannose it is, right? This 9 entry 4I.
Means galactose donor. So
Galactose
beta
donor.
3 and 4.
Oh, okay. Donor is galactose. Yeah, acceptor is this one, mannose.
So in all these cases, when acceptor is having XGLOH, they are getting better selectivity in case of galactose.
In case of galactose, even galactose, if we, as in general talk, we say like the glucose, even though there will be C2 as azide, will get beta more. That is here also we can see. But in case of galactose, C2 azide, then alpha forming more. So, but only case when the acceptor is more nucleophilic, then only they are getting beta more. Other than that, alpha is forming more if this acceptor is poor nucleophile, and the C4 and C3 when the fluorine is present. That this value can be changed like if like the fluorine will change with the other protecting group or the hydroxy group itself.
You go back to previous slide, the mechanism use intermediate before. Yes, here. So here
So,
only
like
yes. How the role of nucleophilicity they are showing here?
Exactly. So once this reactivation is done, now these all intermediate will be in the equilibrium.
Yes.
Alpha triplet is be more stable one.
Okay.
So if nucleophile means acceptor is more nucleophilic, here only the reaction will happen, beta will form.
So immediately that reaction is getting over by SN2 mechanism.
SN2 mechanism. But if our like acceptor is poor nucleophile, then this intermediate will be exchanged with the alpha contact and pair, and again that will go to half chair. Half chair also there will be two half chair in the 4H3 and 3H4. So 4H3 will be stable one, and then again there will be two opening, and then one opening will be favorable because of this giving the product. This will give the chair form, and other opening will give the half chair product.
Yeah. So since acceptor nucleophilicity is less, those cases it is getting
This
time.
SN1 mechanism is following.
Okay.
And giving this alpha product.
Till alpha product.
Sorry?
Alpha and beta both, right? Sometimes beta also, like.
No. What I'm telling is, so if you see here, these two galactose case, beta is more.
Oh, okay,
So
okay, got it,
here
got it.
primary
Yes,
hydroxy means
yes,
nucleophility of the acceptor is more. So
yes.
that is going through here alpha triplet only. If it is poor nucleophile, so the SN2 will not be happen. Then it will come to the SN1 mechanism. SN1 mechanism, there are multiple intermediate. Out of those, so this one is getting activated by 4H13 conformation by using this acceptor, and that is going through the SN1 mechanism. That is giving the alpha product.
Yes.
You go to the last synthesis where they are making this disaccharide or something. Next one after this you showed something, right?
No. That is the just conclusion.
So we are somewhere this 1 minute. Okay, not this one. In pre-activation, they were showing that after decomposition, this anhydrous sugar is forming.
Here.
This case. So how exactly this can form? Because it means that the C6 OBN has to get deprotected, right?
Yes, sir. So what they are telling is, so they are taking this activate like promoter. In that promoter, as the temperature is coming, like here, it will come to -30, -40 degree. So they started with the -78. So at -78, all the intermediate were there. Means this alpha triplet as well as this alpha sulfonyl and the beta one. As temperature is increasing, so since there will be initially whatever triplet that will be is cationic part that will alter this like alpha beta, and once okay, I got your question, like how this C6 getting deprotected and then it's forming.
Because I don't know, this is OBN group, right? It is not as labile as any other. So maybe this oxide, like oxygen is simultaneously first is getting attached. It will form some carbonium intermediate and then
This one.
That is correct.
It advanced low after lead to beta formation in species on the basis of data literature, the characterization and NMR resonance. All three they have given, and a marked increase the relative abundance beta 1 resonance using support their assignment. Identical covalent intermediate also produce alpha activated in other cases. The principal product decompose it 1,6 and hydropyranose 6 formation participating O6 in pre-activation based glycosylation was also observed by others. Formation of 1,6 and hydro bridge by participation of O6. Maybe somehow this O6 is attacking there and this BN group is leaving.
Yes, they're just saying it is previously also observed. So they have done too much thing to explain. Okay, then we'll check the literature maybe.
Hello.
Yes, sir.
Go to the any mechanism slide. So before that, my first question is the whole paper they have used like glycoside, glucoside, or galactoside. So can we call that as that glycoside? Because it is just C2 deoxyazide sugar. I don't know. Can we
It's
call it?
not. If you see the nomenclature, it will be 2-deoxy-2-azido. So
That's what.
just for general term, they are just telling.
But that doesn't makes much sense, right? Like we can't call it as a glycoside, galactoside.
It's not the general nomenclature, yes, sir.
Because if it is azide is in C1 position, that is fine, but it is not the case.
Yes. They are just masking that C2 with the azide. They are not.
Azide.
But they are telling like
Hmm.
azide only, like glucosazide and galactosazide.
Okay. And in the mechanism, like whatever they have shown, based on nucleophilicity of the acceptor, that is very well much established before also. Based on we have seen multiple papers with the similar concept, and they have assigned here acetylene based on the NMR, right?
Yes.
But then how did they calculate the energy difference between there
No. For this
small
energy, they have done this DFT calculation of all the intermediate.
Okay.
Through that only they got this values, energy values.
Other than things are like they didn't do much of DFT based on this one they told conformation and all.
No. They have done all the intermediate DFT. So they calculated all the energy of the intermediates.
Okay.
But in like for these intermediates only, because see this alpha triplet is very much known. This is the stable one. People have detected this one or trapped this one very before itself. So other than this alpha triplet, all the intermediate they have calculated.
So like here also they are showing that if you are using sufficiently nucleophilic one, we will see majorly beta, right? With the C2 azide.
Yes.
But this is the first case, not first case, it's the different case what we see with the other galactose. For that case, any glucose or something, we do see less amount of beta, right?
No others. So in my case also, since I'm using this azide donor in first paper, at lower temperature, we should see like used to see this beta is measured at lower temperature. So there are no as such like nucleophilicity of the alcohol, like acceptor. But at lower temperature, the beta will form more because that is very much like understable, right? Okay, this alpha triplet will be there, and but as temperature is coming up,
telling that as we go to lower temperature, whatever we're just thinking the absence of NGP, that will not have much effect. It's the stability of triplet. Glycosyl triplet is more predominant in lower temperature.
Yes.
Okay.
Like in your cases also galactosazide you guys are using, but you are getting alpha more, right?
Alpha more, true. 80% is alpha only. That is 0 degrees Celsius.
Even though at 0 degree.
0 degree, true.
So
maybe if we go with low temperature, we may get little more beta.
So here also, if you see, these are the poor acceptor, like secondary hydroxy one. Then they are getting alpha more. That means whatever like the way of activation that is going through the SN1 mechanism. In those cases also, not even though there is no fluorine also, the intermediates is going through some thing like this intermediate.
So basically, whether fluorine is there or not, ideally it should go in this way only, right?
Exactly, yes, sir.
So
But I
they
think
can
it
tell,
is
okay, fluorine is not much affecting the reactivity in a different way.
I think
The only
Adarsha, in
thing,
your case, the donor the way of activation is little different. So in
So
that
that's
case,
also
0 degree getting possibility is that directly SN2 substitution of donor itself you are getting may not be this intermediate is forming that much. If you
okay,
go to temperature like kind of pre-activation, then you may observe this intermediate. In that case, the cell reverse. That could be one possibility, because the way of activation is also very critical in this kind of donor.
yes.
Then it will be followed by temperature and other things.
And if, can you go to the 10MR data one, like the VT NMR?
This one.
So like here I see this 3J coupling of C1F na, and that's what I'm seeing, C1 and F. C1 is somewhere else, F is somewhere else. Like
No,
one,
in case of his
one,
alpha,
two.
here only I'm saying like alpha is more desilted one.
No,
In case of
it's not
triplet.
about that one. I'm thinking we are just thinking about the coupling constant, like
No, coupling constant
carbon.
is fine only because see alpha case, this coupling constant is below 5 only. 3.5, 3.6, 4, 4, 3.1, 3.1, 3.3, 3.5. But in case of beta,
No,
it's
I'm not
coming.
analyzing the data. I'm just trying to tell like it is fluorine coupled C1 spectra, na?
Oh, that also you're saying. So that is also
Means
not
like
affecting too much. Even like H1H1, like H1H2 and H1H also almost similar only.
no. I'm trying to more than the data, like different kind of coupling constant. Like if they have taken here means fluorine coupled, that is the spectra. Like
Yes.
if you see the normal 13 spectra, that will decouple fluorine also, that will decouple proton also, na?
Yes.
So they have taken here fluorine coupled proton, fluorine coupled proton spectra. I don't know whether it comes in the normal spectra or not, that fluorine will couple with the hydrogen. And they have taken here fluorine coupled C1, that is the spectra also. And they have indicated the temperature of decomposition also, na, here. Like the
Yes.
range, around 20-degree range they have presented. So that's what the different thing I see.
Yes, I also saw like there is no difference when the like if you see H1 like hydrogen coupling, proton coupling, that is similar to the proton and fluorine coupling.
See, that's also,
That also I had doubt like how like both coupling can be like could lead the same coupling constant value.
True. Because the values are only the I value is same.
Yes,
The
I value
gyromagnetic
same.
ratio and
If you
all of
see other like the nuclei of the fluorine, that is very much different from the proton.
true.
And in NMR, the nuclei matters like how many electrons are present, abundance. But yes, still every case they got the same coupling constant like proton as proton fluorine.
So it almost falls in the range of proton, not almost equal to the proton
Equal to
coupling
the
only. What about the fluorine NMR? I haven't taken. What is the range of fluorine NMR, like 0 to 10, or like how it is? Or 0 to
no.
20, like
It's minus to some I don't know my negative value, but it go to minus sorry plus 300 till 200 plus. Minus
okay.
it go to minus also. I don't know how minus it will go, but it minus 100 to let's say 250 somewhere. Exactly, I don't know the range.
That I didn't have any idea. Okay, that's right.
So that was today's discussion in the carbohydrate discussion series. If you enjoyed the session and learned something new, don't forget to like, share and subscribe for more such research focused talks. Thanks for watching.